Welcome everybody, and thank you for being here today with Fleur and, well, should I say, how do you say in Dutch then? Fleur? Fleur?
Yeah, I say Fleur, but I
Fleur.
actually prefer the French pronunciation. So.
Okay, and Ryan. And so, yeah, they are today's speakers. Ryan Pappalardo, he's an undergrad at Case Western University, and Fleur Vialle from the University of Twente. She now just started her PhD. So let's start with Fleur. Tell us a bit about yourself. What do you do? What are you studying? And what did you study? And what's your project you're working on?
Okay, so for my bachelor, I did it not in Twente actually, but another place in the Netherlands, which was Groningen. It was in the north, and I did physics. And then for my master, I moved on to biomedical engineering, so a bit more to the medical applications. And about 2 months ago, I finished my master assignment and moved on with a PhD project, also at the University of Twente. I basically moved on with the same project that I was doing for my master assignment, and I will tell you a bit about that in my talk.
Great, thank you. And what about you, Ryan?
Yeah, I'm an undergrad at Case Western. I'm in a Dr. Singh's research group, and my current major is chemistry, but this research is kind of more physics, rheology focused. But I'm interested in both, and I hope to go on to do a PhD, but I'm not totally sure on the topic, so I'll have to figure that out at some point soon.
Okay, and what's next? I mean, okay, it's pretty early maybe, but why did you start a PhD, Fleur? And do you want to stay in academia? Do you have an idea? Do you prefer moving to industry? It's pretty early, but you might have an idea about it.
Yeah, so I started the PhD because I just really liked my research, and the PhD position was open and it's basically continuing with the research I was doing. And I also really liked the colleagues and the environment, so that's why I started my PhD. And after my PhD, I'm not sure yet. I might stay into research, but I would also like to get maybe a certain job in a hospital or something, so move a bit more to the clinic, but I'm not sure about that yet. I still have 4 years to figure that out, luckily.
Nice. Well, I don't know if I would ask the same to you, Ryan. It's even earlier for you.
Yeah, I don't really know.
But you said that you'd like to maybe do a PhD, right?
I would, yeah.
Okay, nice. Because just remember, what year of your undergrad?
I just finished my sophomore year, so
Okay,
I'll be
perfect. So,
So sophomore is like a second year.
oh yeah,
yes.
second year.
Nice. Well, I guess we can start, unless anybody in the audience has more questions for our speakers. And so, Fleur, you can start. You can start sharing your screen.
Yes.
It should just stop my presentation.
Okay, let's see. Can you see my screen now?
Yeah, perfect.
Yes, perfect.
Okay, good. So I'll start then. If anyone has any questions, just interrupt me and I'll be happy to answer any questions during my talk. So as I said, I will be talking about what I did for my master project and also what I'm currently doing for my PhD, which is research into the dynamics of ultrasound-driven coated microbubbles confined in viscoelastic capillaries. Well, that's quite a mouthful, so I'll just start with introducing you to some of these topics. And I'll start with ultrasound. So I don't know if you know what ultrasound is, but ultrasound imaging is an imaging techniques in which we use sound waves. These are pressure waves with frequencies in the megahertz range to actually make images. So for example, if you would like to make an image of a kidney, we would use an ultrasound transducer, which you see here on the left. And do I also have a pointer?
We do see your cursor. We see your cursor.
Okay, I think this is maybe better, but
it's even better. Yeah. Perfect.
So this ultrasound transducer transmits ultrasound towards, for example, a kidney. Then the particles inside the kidney scatter this ultrasound back, and this is again received by the ultrasound transducer. And all the signals that the transducer receives from all different particles inside the kidney, it can recombine into an image, like you see here on the right. Well, the main application that we all know is in obstetrics, where we use it to make an image of an unborn fetus, but it's used for many more things. So for example, for diagnosing cardiovascular diseases. So for example, if one would like to image stenosis, which is basically a narrowing of an artery or a vein, or an aortic aneurysm, which is a widening of it, you can also use ultrasound for this. However, blood is a very poor ultrasound scatterer, meaning that where you see the fetus very bright in your image, you will not see blood very bright in your image. And that's why we need contrast agents. So these ultrasound contrast agents are the coated microbubbles that I'm studying. And as the name already suggests, a microbubble is a very tiny gas bubble, which has a diameter of about 1 to 10 micrometer. So you can compare it in size with a red blood cell. And it's filled with usually a heavy gas like perfluorobutane. And this microbubble is coated with phospholipids to ensure that it's stable and does not dissolve instantly when you inject it into the blood. Now here on the right, you see a video of a rabbit kidney, and probably you don't see much right now, but as soon as we inject these microbubbles, you will see that the kidney lights up. So these microbubbles really help with improving the contrast in these ultrasound images. And therefore, we can also really use it to image blood flow. So what you're looking at right now is the aortic bifurcation. So that's the part of the aorta where it splits into two parts, with one going to the left leg, one going to the right leg. And if we inject microbubbles in there, we can actually track them using something called echo-PIV to actually get the flow field. But for all of these, you just need these coated microbubbles. And then, of course, the question is, why do these microbubbles enhance the contrast so much? Well, in regular tissue, you have scattering of ultrasound because of an acoustic impedance mismatch. So acoustic impedance is a material property that is related to the density times the speed of sound in the material. And when you have a mismatch between two materials, so for example, if the ultrasound wave goes from a material with a low acoustic impedance to material with a high acoustic impedance, you have a lot of scattering. Well, this is also the case for microbubbles, of course, because you go from the fluid, which is the blood, to something with gas. But there's an additional part that microbubbles have, namely that they are compressible, and therefore you will have them oscillating. So here on the right, you see a video of this. These are these microbubbles, and when you drive them with ultrasound, they start compressing and expanding. And this oscillatory behavior of these microbubbles really makes them have a scattering cross-section multiple orders of magnitude higher than just regular particles with the same size and the same acoustic impedance. So that's why these microbubbles really enhance the contrast very well and why they're so important. And this oscillatory behavior we can compare with a mass spring system that we all know, where instead of a spring and a mass, we have the surrounding fluid, which is the mass, and we have the gas inside the microbubble, which is the spring. And similar to a mass spring system, which has a resonance frequency, these microbubbles does also have a resonance frequency. And in case that we ignore the coating, this resonance frequency is given by the equation that you see here. And then the main thing I would like you to note is that it's inversely proportional to the radius of the microbubble. This is something we also see in this graph. So on the x-axis, you see the ultrasound driving frequency. And on the y-axis, you see the oscillation amplitude of the microbubbles. Then when you have a microbubble with a radius of 3.7 micrometer, which is this one, you see that the resonance frequency is quite low, which is about 0.9 megahertz. And when we decrease the size of the microbubble, so we go from 3.7 micrometer all the way to 1.2 micrometer, you see that the resonance frequency shifts to a higher frequency. So this frequency is related to the microbubble size. And besides that, it's also related to the ultrasound pressure that you apply. So here you can see the red curves and the blue curves. And when you move from the blue curve to the red curve, so you go to an increased pressure, the resonance frequency drops. So that's part of the response to the microbubble, then another important response of microbubbles is that they actually behave non-linearly. So what do I mean with that? I mean that if you have regular particles in tissue, for example, they are usually linear scatterers, which means that if you drive them with an ultrasound frequency equal to f, then your response will also have frequency equal to f. But if you drive these microbubbles, they will actually respond non-linearly, meaning that you will get both higher harmonics, so twice the frequency back or 3 times the frequency back, and even subharmonics. So that's the half of the driving frequency that you get back. Well, all of these characteristics are very nice and can help us with improving ultrasound and are already quite well described by this complicated equation. So it's quite well known in the community, and on the left-hand side, you see all the inertial terms, and on the right-hand side, you see all kinds of pressure terms. And this equation really describes very well the behavior of these microbubbles when they're driving with when they are driven by the ultrasound. But it is based on one main assumption, and that is that the bubble is in an infinite fluid. And this is where my research comes in, because microbubbles are actually very confined when they are in our bloodstream. This is also something you see here. If you have an overview of our vascular tree, you see that the total cross-sectional area of our capillaries is about 100 times the total cross-sectional area of our artery and veins, meaning that most of the time, our microbubbles will be confined and not in an infinite fluid, and thus the current description by the Rheology equation is not complete. So that brings me to what I'm researching and what I also researched during my master assignment. Namely, what we want to do is measure and model the nonlinear response of these phospholipid-coated microbubbles when they are confined. So how does this confinement change, for example, the resonance frequency of these microbubbles? And we want to do this to make sure that we can increase the sensitivity of all the diagnosing and therapy that is being done with these microbubbles. And also, eventually, we hope to be able to relate properties like vessel stiffness and vessel diameter to the response of the microbubbles, so we can use it as a kind of sensor. Now, for my research, I'm doing both experimental parts and numerical simulations, but for this talk, I will just focus on the experimental part. So I will show you my experimental setup. We have an acoustical part. So that is basically a water tank with a capillary phantom in there and a ultrasound transducer in the front, which both transmits and also receives the ultrasound coming back from the microbubble. And at the same time, we also have an optical setup. So we have 2 light sources on the left, and we have a microscope and a high-speed camera on the right to also optically visualize what's happening to these microbubbles when we drive them with ultrasound. Now, if we zoom in on the phantom that we have, so it should mimic a capillary inside tissue. So we have a hollow tube, which for now is about 100 micrometer in diameter, but we're currently moving down to 15 micrometer. Inside a tissue mimicking material, which in our case is PVCP. And we perfuse this capillary phantom with several types of scatterers. So we have hollow glass beads. These function as our linear reference because we expect them to only give a linear response back. And we have our monodispersed microbubbles, which we are of course using because we want to measure their response. Now, as you see, we use monodispersed microbubbles. That means that the microbubbles are all about the same size, which is very important because, as I mentioned, we want to measure the resonance frequency, but the resonance frequency also depends on the size of the microbubble. So we need them to be about the same size. These microbubbles we produce in-house using a flow focusing device. And you see a video of this on the left. So we have a gas inflow from here, and then from the top and the bottom, we have a liquid flow, which also contains the phospholipids for the coating. And when these all come together in the aperture, microbubbles of approximately the same size pinch off. And this is also what you see on the right. These are this is a curve of the microbubble size that we use for experiments, and you can see that the distribution is quite narrow. So then some of the videos we got from our experiments. So on the left, you see one of the high-speed imaging videos that we got right up till now. So you can see the microbubble in there. It's just not focused enough yet, but you can see the microbubble inside the capillary. And on the right-hand side, you see a typical ultrasound image that we obtain. So basically, you see inside the red box that the signal is quite white. So that means there's a lot of ultrasound scattering. And these are the microbubbles that we're seeing. So we can actually really see the microbubbles here flowing through. So that's good. We have built a setup and we're able to both optically look at the microbubbles and also get an acoustical response from them. Then in order to really get the microbubble response, so really this nonlinear response, we would like to separate the fundamental response, so the response at the driving frequency, and the nonlinear response. So those are the higher harmonics. And for this, we use a technique which is often used in ultrasound named pulse inversion. So in pulse inversion, what you do is instead of just sending a single ultrasound pulse, you send a sequence of 2 pulses, where the first pulse and the second pulse are the exact inverse of each other. Meaning that if you would have a linear scatterer, that the response that you get for the upright pulse, so the regular pulse, would be, for example, this blue curve. And if you would get a response for the inverted pulse, you would get the exact opposite. So now, in the case of a linear scatterer, if you would add these 2 up, you would get nothing, because there's no harmonic response. You only have a linear response. And if you subtract them, you keep the linear response that you already had, but then doubled in amplitude. Now, in case that you have a nonlinear scatterer, so we have, for example, our microbubbles, you will have that the response to the upright signal is, of course, not a linear response, but a nonlinear response. And therefore, the response to the inverted pulse will not be the exact opposite of the one from the upright pulse. So if we add these 2 up, which you see in the purple curve, you see that there's still signal left, and these are higher harmonics from the microbubble. So we want to use this technique to actually really separate fundamental response and harmonic response. So, and this is also, for example, used in tissue harmonic imaging. So here you have an image on the right of the left ventricle, and you see in the top that this left ventricle is filled, by the way, with microbubbles. And on the top, you see that there's no signal there, because you only look at the fundamental signal, and there's much more signal when you look at the harmonic signal, because these microbubbles respond non-linearly. So we wanted to test whether this actually works also in our setup. So here you see the Fourier spectrum, so the frequency spectrum of the acoustic response that we measure for the microbubbles. And you see a peak at 2 megahertz, which is our driving frequency. You also see a small peak here at 4 megahertz, which is just twice the driving frequency. Now, if we use the pulse inversion to only get the fundamental response, you see that we indeed keep the peak at 2 megahertz, but the peak at 4 megahertz disappears. So we really can split the fundamental from the harmonic. Then if we actually add up the pulses, or the response from 2 pulses, you also see that the harmonic response is really enhanced with respect to the fundamental response, which you could hardly see in this first image. So basically, we're using pulse inversion, and it seems to work very well to separate these signals, meaning that we can also better look at the response from our bubbles. So then the actual acoustic response that we get from our microbubbles, you see here that we get both fundamental response and also harmonic response. So we were very happy about this, because that means that we can really measure also higher harmonics. And we just are also able to see a response from our microbubbles. However, as I said, we also do measurements with linear scatterers. So these are our Holder class beads. And we observed that we also get these higher harmonics for the beads, which is not something we expect from a nonlinear response because the beats are not nonlinear. They are actually linear scatterers. So that's basically something we're still looking into because we think it has something to do with nonlinear propagation. And nonlinear propagation is the effect that when an acoustic wave propagates through tissue or through material, that the speed of the peak and the valley of the pressure wave are different, causing the wave to skew and thus to create higher harmonics themselves. And these are, of course, then also scattered by the linear scatterer. So for now, we do get responses, but we're not able to separate the actual microbubble response from the response from nonlinear propagation yet. So that's something we're working on. So that brings me to my conclusion. We've built an experimental setup combining both ultrasound imaging and high-speed optical imaging to measure the response of confined microbubbles. And we tested whether we could use pulse inversion to really separate the fundamental and harmonic response, and this seems to work very well. And now we're busy on actually getting the higher harmonic acoustic response. We observed them both for the beats and the microbubbles, meaning that we still need to reduce nonlinear propagation effects. That was it from my side. Are there any questions?
Yeah, if there is any question, don't hesitate really. Or even in the chat, we can see.
Thank you, Fleur. It was very clear. Thank you.
Yeah, thank you.
So questions? Do we have any questions in the audience?
I do have a question. I hope it doesn't echo too much because I'm in the same office as Aurel. Yeah, I was wondering when your bubbles resonate and when they move, do you know if that is a fully concentric movement or is it more like a wobbling in a plane? Have you
Do you mean whether it's sorry? You mean whether it moves towards the walls or whether it moves spherically, like itself?
Exactly. Like a concentric expansion of the radius, like a compression, or whether it's like a becoming an ellipse in different directions, so to say.
Yeah,
I don't know if I'm explaining myself.
No, I understand what you mean. The bubble will not remain spherical. We really expect it to become, to make nonlinear oscillations or non-spherical oscillations, I mean, because of course you have walls on two sides, or around it, but in 2D you would have walls on two sides, so we really expect it to expand more in the direction of the vessel and not in the direction of towards the vessel walls, basically. And that's also what people observed, yeah.
Nice. So you've been also working on modeling the pressure a bit differently than a couple of months ago and all that, right?
Yes, I'm working on it. So these non-spherical oscillations will definitely be also in the simulations.
Perfect. Cool. Well, best of luck with that.
Thank you.
Abby, please go ahead.
Hi, Fleur. This was a really interesting talk. Very clear, as Michelle mentioned. So this might be just a stupid question. So when you do ultrasound, is it important? So I mean, one way to think about gas bubble is our deformable particle, right? Mm-hmm. In some sense, not exactly, but what if you had some sort of rigid particles in your system? For the ultrasound to work, does it really matter that if you have rigid or deformable particles?
So in principle, ultrasound also works if you have rigid particles. So that's also why if you, for example, make an image of a fetus or something, you also still see stuff. But these microbubbles, because they oscillate, they actually kind of re-radiate the ultrasound and therefore really enhance the signal from the ultrasound that you get back. So it's mainly, it also works with rigid particles, but it's really enhanced when you use particles that can oscillate. Is that an answer to your question?
So the oscillation in terms of changing shape?
Yeah. So the microbubbles really expand and compress basically due to the ultrasound that's driving them.
Okay, thanks. Thank you.
In regards to that, and also Pablo's question, so the whole system is really a 3D model that you have to build overall, because you have those two radius. And I was wondering, how will you try to model also the viscoelastic material around it?
Yeah, that's a very
Yeah.
good question. We're actually still working on that right now.
Okay.
So so I'm working together with Pablo and Aurel in yeah, you know them. So we're either gonna just make some thin walls around it and put their viscoelastic solid equations in there. So we have the hyperelastic one already, but we still have to put viscous parts in there. Or the other option, what we're gonna do is we're gonna create some kind of ghost boundary on which we put some boundary conditions to really get this viscoelastic behavior in there. But we're still discussing how to do this.
Okay. Best of luck also to do that. And I really hope to see your work in the future, because it's promising, really. Thank you.
Just one question out of curiosity. What about numerical simulations? What method do you think you're going to use, or have you already chosen your numerical approach?
Yeah, so I'm working together with CMF, so with CMF from Impari, and they have a simulation library, SimLib, and I'm using this. So it's based on finite elements simulations, and what we're currently doing is, wait, I maybe even have slides of this. Let me check. So basically, this is the framework that we have. So we had it in 2D, and I'm currently having it also in 3D. So what we basically have is we have a fluid domain in which we just use the Navier-Stokes solver to solve the fluid dynamics, and we have walls around it which are currently hyperelastic. So we're solving hyperelastic solid equations for that. And inside this fluid domain, we have a void, which is my microbubble, basically. And then we are modeling this microbubble behavior by taking all the pressure terms that I showed in the Rayleigh-Set equation. I put this as a boundary condition on the boundary of this bubble. And that's how we are modeling it. So
nice.
Yeah.
Okay, so the interface between the fluid and the particle is perfectly meshed.
Yes.
Okay, perfect. Thank you. Okay, if there are no more questions, I guess it's time to switch to Ryan.
We'll stop sharing my screen.
Yes,
So
sounds
Ryan,
good,
you can go ahead and start sharing your slides.
Okay.
Great.
So can everyone see this well?
Yes.
Okay, cool.
Perfect.
Yeah. Okay. So yeah, my research is on the microstructure of attractive and frictional dense suspensions. And the way that we are investigating this is through shear reversal. So just as a brief introduction to dense frictional suspensions, a dense suspension is a suspension in which the volume fraction of the solid is greater than 50%. However, that's for a three-dimensional case, and all of our data is from two-dimensional simulations. So in practice, we focus on volume fractions a little bit higher. So for instance, all of our data for this presentation will be at 70% volume fraction. And a dense frictional suspension is one in which, while the fluid will lubricate the particles, it will only do so at low stresses. So once you have a large enough stress to overcome that lubrication force, you have what's called lubrication breakdown. And at that point, the surfaces of the particles will contact each other. And since there is a frictional force between those, that can change the flow characteristics. So the two probably most popular examples are shear thickening and shear jamming. So in mild cases, you can have shear thickening where the viscosity will increase as you increase the stress. But if you have enough volume fraction or enough friction, you can also have shear jamming, where you push it hard enough that it becomes fully solid, similar to what oobleck does. Right. And so, like I said, we focus on shear reversals, which is to say that once you apply a stress to your system for long enough to reach a steady state, you reverse the direction of the stress. So you apply the same magnitude of stress, 180 degrees reversed. And there's a fairly decent body of work for shear reversals. These two graphs come from a 2016 paper, but traditionally the focus has been on the friction forces, the hydrodynamic forces, and occasionally some repulsive forces. So before we go too far into it, we can talk a bit about our simulation scheme. So we focus on lubrication forces and friction, in addition to interparticle forces. We can talk a bit more about that later. So just a brief overview, the lubrication force is the force which attempts to keep the particles separated. So you can see here, as they are moving towards each other, there is a force which attempts to push them back apart. But if the stress is large enough, again, that force can be overcome and you end up with a contact force. So the contact force has both a normal and tangential component, and then both of those contribute to the rheology of our materials. And because we assume these particles to be inertialess, we assume that the sum of all the forces, so contact, lubrication, in addition to our repulsive and attractive forces, we assume that these all sum to zero. And that is sort of the foundation for where all of our simulation data comes from. Yeah. So these are the force profiles for our attractive and repulsive forces. So it's plotted as a function of interparticle distance. You can see that green solid curve there is our repulsive force. So it is exponentially decaying. So it's only very significant for small gaps between your particles. You can see as the x-axis progresses, it gets weak fairly quickly. And we also have this blue curve here, which is our attractive force if we define it as F sub A is equal to 0.5 R, which means that at zero separation, the attraction is half as strong as the repulsion. But since it is van der Waals-like, it decays quite a bit slower. So even for F of A is equal to 0.5, it starts below the repulsive force, but as your gap widens, since it decays slower, you end up with the attractive force being stronger. You can also define F of A is equal to 2R. These are just examples. You can define it to be whatever you like. So for F of A is equal to 2R, it starts stronger than the repulsive force and stays stronger for essentially any interparticle separation distance. Yeah. So as we talk about shear reversal, so the first thing I should mention is that with these attractive forces, you get what's called a yield stress. So yield stress essentially means that a yield stress is a threshold stress such that if the applied stress is below your yield stress, it won't flow like a traditional suspension. It will act as though it's a solid material. And only when you apply a stress which is larger than your yield stress can you observe flowing behavior. So the three regimes that we focus on are when your applied stress is below your yield stress, and in that case, flow doesn't occur at all. So this x-axis here is strain, or like displacement of the system. So you can see this red curve has essentially no strain, it doesn't flow, and the viscosity diverges to infinity fairly quickly. So that is the regime in which flow just doesn't occur. The second regime of interest to us is when the applied stress is larger than the yield stress, but not by much. So it's fairly close to that unyielded state, and we see a fairly high viscosity in that regime. So this is when the attractive and repulsive forces can still induce fairly strong force networks before they're overcome by larger stresses, which is what happens in the third regime, which is when the applied stress is much beyond the yield stress. We see that the viscosity drops quite a bit because the stress is so large such that these attractive and repulsive networks sort of get overwhelmed by the applied stress. And so viscosity only is really coming from the contact forces between the particles. So as a way to sort of re-emphasize that, we can look at the frictional contact number. So this is the average number of frictional contacts between particles. So for our green curve here, this is our very high stress regime. And we can see that there's a lot of frictional contacts because that stress is high enough to overcome the lubrication forces, and therefore you end up with a large number of frictional contacts. However, if you plot the same thing for the applied stress being only slightly above the yield stress, you see that we have almost no frictional contacts. You know, one or two particles may collide somewhat randomly, but there's no consistently high level of contact force, and therefore you can assume that the viscosity is mostly coming from attraction and repulsion. So because these are all simulated, we have access to the data, which tells us which forces contribute to viscosity. So we can see what we were saying previously, where in this very high stress regime, we have the contact forces dominating. So you can see that the blue curve here, which represents your contact force, is contributing most of the viscosity to the system because the stress is large enough such that they can actually contact and resist the flow very effectively. However, for this lower stress regime, we can say that the attractions and the repulsions will dominate. Because we have this lower stress, these attractive force networks and repulsive force networks are still able to set themselves up and be able to resist the flow. And so most of the viscosity will be coming from attractions and repulsions. So you saw in the previous slide, or 2 slides ago, that we can use the frictional coordination number, or the average number of frictional contacts per particle, as a useful analog for how those contact forces are contributing to the rheology. So for our purposes, as we focus on multiple forces, it's helpful to define coordination numbers for multiple different types of forces. So for our purposes, we're focusing on contact forces, attractive forces, and repulsive forces. And so when we look at all of our interparticle interactions, they are all sorted into one of these 3 categories. So if 2 particles are in contact, we say that they are frictionally coordinated and they're put in the contact category. If they're not contacting each other, we say that the relative strength of the attractive and repulsive forces will determine which type of coordination it is. So with a stronger attractive force, we say it's attractively coordinated. And with a stronger repulsive force, we can say that it is repulsively coordinated. Yeah. So once we define these different types of coordination numbers, we can plot them as a function of the interparticle distance. So we can say that for lower strengths of attraction, or actually for either strength of attraction, you can see that attractive coordinations dominate at these larger interparticle distances, which should make sense because if our attractive force is going to decay slower than our repulsive force, you would expect that for large separations, the attractive forces would be dominant, which is what you see here. However, when those repulsive forces do dominate is in the very, very small interparticle distance regime. And we can see that for weaker strengths of attraction, that is a wider band. So if the strength of attraction starts out 1/10 of the strength of the repulsive force, we can see that we are able to form more repulsive coordinations because it takes longer for it to be overpowered. Whereas when we start with 0.5, that blue band is quite a bit narrower. And so we have less repulsive coordinations because it's overpowered by attraction a lot faster. This is the viscosity as a function of stress. So we can see for these different strengths of attraction, we see fairly different behaviors from the system. So for no strength of attraction, we have our lowest viscosity. As we move up slightly to a fairly weak strength of attraction, we do see some increases in viscosity, but it's mostly in the low stress regimes. So we have that increase in viscosity is basically limited to where the contact forces are not super prominent. And as we go to a higher strength of attraction, we see something similar where we still have that increase in viscosity. However, it's mostly in the regime of low stress, and the increase in viscosity is more minimal as you move to the higher stress regime. We can also see that the yield stress will increase with the strength of attraction. So that tendency to not flow until enough stress is applied, that scales fairly well with the strength of attraction. So as you increase that force, you increase the necessary stress on the system to induce flow. All right. That is the work that we have currently. For a bit of comment on our future plans, we want to continue to explore the force networks that sort of set up these rheological behaviors and see how they change under reversal. Specifically, we're hoping to take some analysis tools designed for like rigid cluster analysis and hope to generalize them to attractive and repulsive forces. And we also want to do some more work on analyzing different loops and their structure, and sort of, if we could use that as a tool to get more of a distinction between shear jam-in behavior and yield-in behavior. And while it's not a super large priority at the moment, in the long term, we would consider adapting whatever results and tools that we develop into 3 dimensions, just for it to be a little closer to physical reality. So yeah, thank you for listening. Any questions?
Thank you, Ryan.
Thank you, Ryan.
That was great and very clear too. Questions? I do have some questions, but there might be some conflict of interest here.
I think you can ask your question because
I'm gonna
ask question to Fleur, so I think that's okay.
I'm gonna break the ice. I mean, I'm gonna ask questions of some of them. I already know the answer, but I think it's useful. What's the size of the systems you're studying here?
Yeah, very good question. This data is all for 2025 particles.
And it seems that you have Lees-Edwards boundary conditions, right? And another question, how do you define the yield stress when you say below, at, or above the yield stress? How do you find the value for that yield stress?
Good question. So I can go back a little bit. Yeah, here. So right now the approach is, so here we have 3 different stresses plotted. The simulation spits out however many you want. So usually we'll pick 20 or 25 different stresses. And the yield stress is basically just defined as the stress at which it begins to flow. So with these 3 stresses, that wouldn't be a super accurate measurement. But when we run these simulations and we have, 20 or 30 different stresses, especially if we sample very finely in the yield stress region, we can essentially just say the yield stress is the first stress which exhibits consistent flowing behavior.
So you actually just measure it. And how many simulations do you do to do that?
We usually do like 20 different stresses, and then
I mean for each stress.
Oh, like how many realizations? At the moment, just 1 for each one. We're still kind of in the position of like figuring out what's worth investigating. Once we're a little more zeroed in on like, this is what we want to work on, we would run many more trials to sort of get smoother data.
Here, Rahul, please go ahead.
Hi, Ryan. It was a great talk. I just have one question, like in this plot and also in like few other plots. At gamma equal to 5, that is the strain unit equal to 5, you have the shear reversal, right?
Yeah. So that drop in viscosity.
Yeah,
is
drop in viscosity or
because of
drop
that.
in the number, I guess. So won't it be like, it's just a suggestion or a comment? So won't it be like a good point to have it simulate for 5 more strain units so that like you can average out the properties for before the shear reversal happens and after the shear reversal?
Yeah, that's a very good point. So here the data is just cropped essentially to have a bit of a cleaner image. In reality, yeah, that's a very good point that we usually run it for at least 5, sometimes 10 more strain units after reversal, essentially for that reason, to make sure we have enough data to actually make meaningful conclusions.
Okay, yeah, got it.
Yeah, so
Thank you.
normally we do it's just cropped here.
Got it. Yeah, thank you.
Yeah, good point.
But in general, also for the EU stress, I think it's very valuable to do multiple runs for the same stress, because you know all of these behaviors, jamming, yielding, they're more of a statistical behavior in the sense that even jamming, you have a probability of jamming for a fixed volume fraction. It's not that you always have jamming for that specific volume fraction.
Yes,
So it's actually very hard to identify those points. Okay, are there any other more questions here?
Just a question regarding to experiments. Do you think that you can, you will try those, or you think that someone in your lab will try it to compare, or
at the
is it not
moment,
the
I
scope
don't
at
think-
all? Maybe it's not, because it's super difficult to measure these kind of forces. And I know
Mhm.
it's completely different for experiments than for simulation, but just to know.
Yeah, it would be super cool too, but I don't think anyone in our lab has
Okay.
plans to do any experimental work. So
I know people in Toulouse, they're doing some experiments, sorry,
Okay.
but it's more about adhesion. These are more van der Waals type of interactions, and they're not just in super short flow, but also pipe flows, and it's not easy.
Yeah, of course, I know.
It's not easy. It's not really. I mean, it's here the power of these simulations is that you can split every component.
Yeah.
In reality, it's pretty hard to do so.
Okay, just by curiosity. Thank
Yeah.
you so much, Ryan.
Yeah, thank you.
Okay. Well, if there are no more questions, we're gonna stop the recording here.